Okay, so the coolest part of this unit, I think, is how our eye works. So first we need to draw an eyeball. So this is the upper part of the eyeball. This is the lens. And at the top of the lens and the bottom of the lens, there's a muscle. The lower part of the eyeball. And then back here coming off is the optic nerve. And the optic nerve is what carries the image that gets formed by our lens to the brain. And that image that gets formed by our lens gets formed back here on our built-in screen. And this built-in screen, that's really three-dimensional, even though I'm just drawing it as a curved line here. This is our retina. So this is where the image forms. Now, an interesting little side note, where the optic nerve comes off is really the blind spot on our retina, because it's kind of like, imagine a camera that has like all these pixels where the image is formed, but in one spot there's no pixel there because the optic nerve comes out. So any part of an image that's formed on that little piece where the optic nerve comes out is actually a blind spot. These guys are our muscle. And the muscle's job is to stretch the lens thin or to relax and let the lens go thick, depending on where the object is, so that the image of that object will get focused on the retina. Because as the lens changes thickness, it's going to change focal length. The thicker the lens, the shorter the focal length. The thinner the lens, the longer the focal length. Because the thicker the lens, the more it'll bend the light. Okay? Now, if the retina is our screen, it means that our image is real, right? And if our image is real, it means it's formed upside down in our retina. And it is. And yet we see right side up. But that's because the optic nerve carries the image, which is upside down, to our brain, and our brain flips it over. Okay, now I was in grade 3 when I learned this. And from my older sister who was learning it in bio class. And I can remember for days and weeks and even months after, when I would first wake up in the morning, I would lie really still and think, okay, maybe if I open my eyes really quickly, my brain won't know I'm awake and everything will be upside down. It never worked. And then when I would be in class and I'd be bored, I'd blink really fast to see if I could like catch everything upside down, if I could blink faster than my brain could turn it over. That never worked either. Although sometimes when I'm in meetings these days, or not these days, but like still at this age of my life, sometimes I blink really fast just in case. The other cool thing is there was a study done about 15 years ago that I remember reading about. And it just shows the amazing instrument our brain is. And in this study, they were studying the adaptability of the brain, and they put a pair of goggles on the participants, and the goggles flipped the image over. Everything you were looking at then was flipped over so that it ended up being right side up on your retina. And so then when the optic nerve carried it to your brain and they flipped it, you would see it upside down. So like the book you were reading would be upside down. And the cool part of that study was it didn't take very long before the brain stopped turning the image over. The brain realized that for some reason it was already right side up. Imagine like how cool our brain is, like totally on its own. Now, I also think the brain was probably tricked when the participants took the goggles off, because they'd be like, okay, come on, make up your mind. You want me to flip it or not flip it? Anyway. All right, so back to our eye. So the muscles stretch and compress the lens depending on where the image is. So if the image is far away, and remember, images that are far away, if the object is far away, then light from a distant object comes in parallel. And when it comes in parallel, it needs to get, the image back here needs to be formed on your retina, right? And if it's not on your retina, then what we're going to see is going to be blurry. So this lens, because the retina's all the way back here, this lens needs to be stretched pretty thin, so that these guys don't converge too quickly, that they converge slowly and end up forming the image on the retina, right? The thicker the lens, the faster the rays are bent, and it's going to get, the image is gonna get formed in front of the retina. So we need to stretch it really thin to get our image back here. Now, it is very possible that many of us are not able to do that. So this is the healthy eye. And sometimes one of the reasons we can't do it is like as we get older, our muscles don't work as well, and so we can't stretch the lens thin enough. The image ends up in front, and life is blurry. Sometimes, if we have eye issues from the time we were young, it might be that our lens and the length of our eyeball don't really match. They're not really in sync, like our eyeball might be too long. We can kind of help our lens a little, and those of you sitting in the back of the classroom that see the board is blurry, this could be your issue. And sometimes when we see something blurry, we squint to try to see it better. And what squinting then does is we try to pull our retina up closer to where the image is. Since we can't get the image all the way back there, then let's try to pull our retina up to help it. But if any of you have ever done this, you can't squint for very long before you get a headache. And that's really a sign you need to go get corrective lenses to help you. So that's for images or objects that are far away. For objects that are near, the light rays don't come in parallel. They actually, so like if here's my object here, the light rays, when they strike the lens, are actually going to be diverging. And so in order to bring them together in time to get them on the retina, we need a lens that's even thicker. So our muscles need to relax so these light rays can converge on the retina as opposed to in behind. Okay, so if I can't get my lens thick enough, they're going to not come together soon enough. Okay, again, if that happens, I need a corrective lens. So there's really three main issues with our eyes. One is called nearsightedness. And nearsightedness is actually exactly what the word implies. It means we can see near objects. Some people think nearsighted means you can't see near. Well, then it would be called non-nearsighted. So you can see near objects, but you cannot see objects that are far away. Okay, if you can't see objects that are far, then it means we can't stretch this lens thin enough. Okay, so cannot stretch thin enough. And if you can't stretch it thin enough, then the image is going to land in front of the retina and it's going to be blurry. So here's my lens. Here are my parallel light rays coming in from my object. Here's my retina. And because I can't get it thin enough, these converge too quickly. And my image is here. What do I need to do to fix this? I need to put a lens in front that's going to spread these guys out some. It's going to spread them up here so that then they'll take longer to come together. If I want a lens that's going to spread light rays out, then it needs to be a concave lens or a diverging lens. Okay, so that's the first eye issue. The second eye issue is its counterpart, farsightedness. And farsightedness is the exact opposite. You can see far objects, but not near ones. If you can't see near objects, then it means you can't get the lens thick enough. The muscles can't relax enough to get this lens thick enough, and so the image is going to land beyond the retina, right? And so we can't get them to converge enough. So they're coming in like this. The retina's here, and but they're converging back here. Okay, so what do we need to fix this? We need something that's going to help us converge them quicker. We need a converging lens in the front that's going to cause them to come down a bit before coming in to our own eye's lens, so then it will form on the retina. So we need a convex lens or converging.